In Chapter 3, we talk about some special multimedia services in IP networks. And we have traditional services, internet services, and some call it legacy internet services, like Telnet for remote console, file transfer, FTP, message exchange, and some call it elastic services because there's no upper limit for the end-to-end delay in a wide range. For example, in TCP, the first timeout for retransmission is set to 3 seconds, which is enormous in IP networking. And we have timer-controlled protocols. And these traditional internet services are insensitive to loss or delay. Either they handle it in application when using UDP as transport, or they control it by TCP for reliable transmission. When it comes to real-time services, we have some special requirements and needs. First is bandwidth requirement. If you have a multimedia service, you need a minimum bandwidth to support streaming. And this minimum bandwidth is influenced by the codec you use, the resolution you have or the sampling frequency you have, and the encapsulation overhead, which is added to the samples. Real-time services are also tolerant to packet loss. If a simple voice sample would miss in a voice communication, maybe you wouldn't recognize it, you wouldn't hear it. And same is true for video. If some tiny information is missing in a video, maybe you don't see it. It's different to file transfer where 100% of the bytes must be transmitted. And real-time communication and multimedia communication is less tolerant to delay and delay jitter, because at the time when you start to play out samples, you must receive missing samples in the background so that the playout is not interrupted. If the transmission is not fast enough in the background, your communication will freeze. Maybe you know it from YouTube sometimes. It freezes and then it loads in the background, and from time they start again when they received enough samples. So the difference in service requirements is clear. And here is a table for some applications just with some rough idea. In emails, it's like file transfer. We have high loss sensitivity. Therefore, it uses TCP as transport. End-to-end delay sensitivity is really low. Whether you receive an email in 1 second or 3 seconds, don't care. Jitter as well. And the bandwidth requirements, email works from very low bandwidth connection up to very high bandwidth. So we don't have any special requirement. Same is true for other applications like file transfer. For file transfer, maybe we should have a minimum bandwidth so that we don't wait too long. The same is true for web access. And looking to other applications like multimedia applications, low sensitivity to loss up to a special level, not to an ultimate level, but if the loss probability is small, then we don't care. Same is true for delay sensitivity for audio on demand. And video on demand, it's similar. You just wait until you received enough samples and then you start to play out. For interactive multimedia, it's different. Loss sensitivity is low again, but delay sensitivity is now high. Jitter sensitivity is high. And depending on the volume you have to transmit, in telephony, the volume is quite small, so bandwidth requirement is small. But for video, bandwidth requirement is high because the size of a video is much larger. To show how voice over IP is created and encapsulated, I show you here an example for the PCM, pulse code modulation, with the special form of the G711 codec. Voice is an analog signal, so always you have to sample this signal, you have to quantize this signal, and you have to code this signal. Whether you first quantize and then sample, or whether you first sample and then quantize, it leads to the same output. You have some digital values at discrete times. And you can encode it now, and this means you have at a special time some code for a sample. In the G711 codec, the bandwidth of the analog signal is limited to 300 Hz up to 3.4 kilohertz. So 3.1 kilohertz is the bandwidth for the signal. And we use the Nyquist criterion for sampling, and this means the sampling rate must be twice the bandwidth of the signal in minimum. For G711, the sampling rate is 8 kilohertz, and this is more than twice the bandwidth of the signal. And this leads to a situation that every 125 microsecond, one sample is created. The G711 codec works with 8-bit samples. By 8-bit you have 256 amplitude levels you can separate. And it's a special nonlinear quantization here with A law in Europe and mu law in US and Japan. This leads to 1 byte every 125 microsecond samples. Just remember, in voice codecs, we collect samples for 20 milliseconds before we encapsulate these samples in an RTP packet. On application level, because we create 1 byte every 125 microseconds, we create 64 kilobits in 1 second. So we have 64 kilobit per second load generation in this codec. This is the original ISDN codec with 64 kilobits per second application level samples. In IP communications, we must encapsulate these samples. So we gather samples for 20 milliseconds, some call it chunk. And then we take these samples and encapsulate it in RTP. In 20 milliseconds, we will have 160 samples, each sample 1 byte, so 160 bytes. We add 12 bytes of RTP header here. Then we have an RTP packet of 172 bytes. This RTP packet is encapsulated in UDP. UDP has 8-byte header. We remember now we will have 180 bytes on UDP level. And this is encapsulated in an IP packet again. And we add the IP header to this construct of UDP. And by that, we get an IP packet. If it's IP version 4, the header has a size of 20 bytes. This means we have 200 bytes in such an IP packet. And the next IP packet will have the next 20 milliseconds of samples. The question is, which bandwidth is required for such a voice over IP stream? What we must keep in mind is that we do sample and that we do encapsulate. This will include some delay into the process and will add some protocol overhead. Looking into the size of the different protocols, we have RTP with 12 byte, UDP with 8 byte, IP version 4 20 byte, or IP version 6 with 40 byte. Let's keep with IP version 4. And this IP packet must be encapsulated in a frame of layer 2. And first idea is to encapsulate it in Ethernet, local area network technology. Then we must add 14 bytes of header and 4 bytes of frame check sequence. And this means we have 218 bytes of a frame every 20 milliseconds. And this is a bandwidth on layer 2 of 87.2 kilobit per second. If we would encapsulate this IP packet into an Ethernet on a trunk with VLAN tagging, then the VLAN tag adds 4 bytes to the Ethernet header, and have 222 bytes every 20 milliseconds, sums up to 88.8 kilobit per second. A rough estimation for voice over IP stream is that with G711 encoding, you need less than 100 kilobits per second for each IP flow. Here's a list of some voice codecs you might know from some applications. We looked into the PCM codec and it has 64 kilobit per second on application level. There are some codecs which compress, and you can see some of these codecs compress very hard. This effect is not really that much on layer 2 because also for this compressed codecs, you must encapsulate these samples, these data into RTP, UDP, IP, and layer 2. And the deduction of bandwidth requirements is not that much on IP level compared to the rate reduction on application level. In this table, you find some more information, especially the mean opinion score, which means the subjective quality for such codecs on application level, where 5 is excellent and 1 is unsatisfactory, and this is part of AMC class. Looking into video over IP, it's same but different, because in video over IP you also create samples, and each picture of a video, and video people call these pictures frames on application level. So each video frame is one sample and must be encapsulated in RTP, UDP, IP, and Ethernet as well. But one video frame very often has more than 1460 bytes. So you have more than one RTP packet for one video frame. And when it comes to this video encoding, it depends on the codec you use. For example, with H265, we have capabilities of 4K videos, and these require 20 to 30 megabits per second in an IP network. In H264, we have a very huge scale how you can encode video, and for this you can start with 5 kilobits per second, tiny video with high compression, and for IPTV it sums up to 8 megabits per second, HDTV quality. Older codecs require higher bandwidth, and MPEG-1 has less than MPEG-2 because the screen size was smaller. We have also different video frame types. For example, an iframe with 300 kilobytes, an IPTV, and a P-frame with 30 kilobytes, and a B-frame with 7 kilobytes. Remember that in voice you have several samples in one packet, and in video you might have more packets for one sample. Finally, let's talk about some signaling in IP networks. And signaling is used to control application level sessions and to negotiate capabilities. In IP networks, we have some end-to-end communication, we have some initiator and responder, or calling party and called party. And we initiate some communication either by a request response like HTTP or some session setup. And we have some addressing on layer 7 like the uniform resource identifier in HTTP or something different, your email address for example. We select content we want to share and we start communication, we stop communication. There are two ways to control such sessions. One is in-band signaling and one is out-band signaling. In-band signaling means the control message and the content itself are embedded in the same protocol, like in HTTP. You send an HTTP GET request, and with HTTP 200 OK response, the web page you requested is delivered. This is in-band signaling. Out-band signaling means we use a separate protocol to control sessions, and some protocols from telephony we know signaling system number 7, and in IP networks we know SIP and SDP, session description protocol. This is used for the control of sessions, and encapsulation of media data is done by RTP-UDP. In this picture you see some signaling using SDP or real-time streaming protocol as well. Then it might use some TCP or UDP encapsulation for transport, and then on IP layer we have the IP addressing, and on physical layer it depends which media you have different options. Media is encoded and sampled and then encapsulated in RTP, UDP and IP. Some examples of signaling options is given here for the application WebRTC. In WebRTC you might use WebSockets. You don't need any signaling infrastructure, but you just use the WebSocket to create a proprietary implementation of signaling. Then there's some XML HTTP requests with JavaScript you can use. You can use some SIP, session initiation protocol, over a WebSocket. You might use XMPP, extensible messaging and presence protocol, for example in Jabber. And you might have some in-band data stream which is proprietary. Another example is if you look into the well-known video LAN client VLC. It has capabilities for HTTP, RTP raw socket, MMS, Microsoft Media Server, RTSP, real-time streaming protocol, HTTP with JavaScript, and HTTP RESTful API. These examples shall show you that we have needs for signaling and we have different mechanisms to implement it.